Statistics courses often teach the two-sample t-test, ANOVA, and linear regression as very distinct approaches to looking at different types of data. In this video, we're going to make connections among these by focusing on the statistical models. Statistical techniques taught in introductory statistics courses typically have one response variable and one explanatory variable. The response variable measures the outcome of a study, and the explanatory variable explains changes in the response variable. In addition, each variable can be classified as either categorical or quantitative. Categorical data places individuals into one of several groups, while quantitative data consists of numerical values for which most arithmetic operations make sense. So in your introductory class, you often talked about techniques that would work for each one of these categories. For example, if the explanatory variable is categorical and the response variable is categorical, you often did a chi-squared test or a two-proportion test. If the explanatory variable was categorical but the response variable was quantitative, you did the two-sample t-test or ANOVA. And we looked at that in the last video. For example, we had two types of batteries, generic or brand name, that's categorical explanatory variables, but the response variable was time until the battery failed. That's a quantitative response variable. When both the explanatory and the response variable are quantitative, we use regression. And when the explanatory variable is quantitative, but the response variable is categorical, we look at logistic regression. Logistic regression and ANOVA are often not covered in introductory statistics courses. We will talk about them later in this course. In the previous video, we developed a model for a two-sample t-test, and we showed how statistical models have the form observed value equals a mean response plus random error. For example, in the two-sample t-test with batteries, again, this is a very small sample, just so you can see the mathematics behind it more than actually analyze this data. We had 4 generic batteries and 4 brand name batteries, and we measured how long those batteries lasted. We write that model as our observed value, just the data we observe in our study, is equal to some mean response. Here, the mean represents either the mean of the generic group or the mean of the brand name group, plus some error term. Plugging in our actual observed data, we can see exactly where each number comes from in each one of these 8 equations, where we have 2 groups. I represents the 2 groups, and J represents 4 observations in each group. In reality, we have 2 unknown populations. Mu1 represents the mean time, or the mean number of hours, that a generic battery would last, and Mu2 represents the mean time that a brand name battery would last. We took a few samples from each of these populations and calculated a y bar. We often write y bar as mu hat, where the hat indicates that we're estimating the true population parameter mu. We don't know what mu's are, but we can calculate y bars, or sample statistics, to estimate what the population parameters are. So in essence, we can generate a null hypothesis that says we are testing whether the mean of population 1 is equivalent to the mean of population 2. If the y bars are relatively close together, we have no reason to reject this null hypothesis. But if the y bars are far apart, we can reject the null hypothesis. It's important to recognize in every hypothesis test, we can't just look at the mean values. We also have to look at the standard deviation, or the error terms. So in this case, our error term represents how far apart the points are from our overall mean value. And again, we only have estimated error terms. We observed a value, 1 battery lasted for 90 hours, minus the mean value for the generic group, and we had a residual of 10. The true error term would be 90 minus the mu1 value, and since we don't know mu1, we don't know the true errors, but we do have residuals which help us estimate those error terms. Thus, we've developed a model for a two-sample t-test which takes into account the true group means and random error. But here we have our sample data. We can also write it in terms of population parameters. And we use our sample mean and our sample residuals to calculate a standard deviation to determine whether we can reject or fail to reject the null hypothesis. In ANOVA, we use a slightly different model. Instead of using 2 group means, we break the response into a grand mean, mu, plus 2 group effects, alpha 1 and alpha 2. Mu hat, which is the estimate over the overall mean, also written y bar, is just 82.5, and we have alpha 1 and alpha 2, which represent the effect size. the way we can think about this is we know that the average battery has an expected lifespan of 82.5 hours. If we know that the battery came from group 1, the generic group, we know the expected lifespan decreases by 2.5 hours. If we know the battery came from the brand name group, the effect is that we have an increase in the expected lifespan of 2.5 hours. You notice that these mathematical equations are absolutely equivalent to what we did in the two-sample t-test. It's just a different way of breaking the data into different groups. We often write this as our observed data, Yij, is equal to some overall mean, mu hat or y bar, plus the effect size, plus the error terms. So visually, the way we can think about this is we have an overall grand mean of 82.5, and we can measure the effect of being in group 1 as negative 2.5, and the effect of group 2 as an increase of 2.5. So in our two-sample t-test, we typically had just Yij equal mu I plus epsilon ij. In the ANOVA, we have mu plus alpha I, so we have a grand mean plus the effect sizes. In the two-sample t-test, we use mu1 equal mu2, but here we can show that mu1 is really just mu plus alpha 1, and mu2 is really just mu plus alpha 2. So testing mu1 is equal to mu2 is equivalent to testing if alpha 1 is equal to alpha 2. They're mathematically equivalent. When we write a null and alternative hypothesis in ANOVA, we usually focus on the effect sizes. Are the effects essentially zero, everything equivalent to the grand mean? Or we can also write that equivalently as, is the effect of group 1 equal to the effect of group 2? Instead of using two group means in regression, we create a model for a straight line using the y-intercept and the slope. Instead of having two subscripts, an I and a j, we only have one subscript, and we use the x variable as either a 0 or 1 to indicate which group the data fall within. Notice that when x equals 0, that would be the same thing as mu1. When x equals 1, we can represent mu2 as beta naught plus beta 1. Thus, if we write the hypothesis test, mu1 is equal to mu2, which we do in the two-sample t-test, equivalently mu2 minus mu1 equals 0, that can be written as beta naught plus beta 1 minus beta naught, which can be simplified again to the null hypothesis that the slope coefficient, beta 1, is equal to 0. So again, we've shown that testing for a difference in the two-sample t-test is the same as testing whether the slope coefficient is equal to 0 in the special case when there are only two groups. So if we look at this visually, we have our generic group and our brand name group. In regression, we define those as x equals 0 and x equal 1, and we create a regression line to fit our data. So in this example, if the mean of the generic group was equivalent to the mean of the brand name group, we would expect our sample data to demonstrate that the slope was essentially 0. So again, we can look at the entire data set through a statistical model where the expected y-intercept is equivalent to the expected value when x equals 0, and the slope is the change we expect in the response when we go from x equals 0 to x equals 1. So many times we see a regression model that looks like this. Our observed data equals beta naught hat plus beta 1 hat xi plus our estimated residuals. In the previous equations, we were still showing residuals, so the model was representing each observed value. To create an equation for a line, we use a y hat to say the expected response is equal to the y-intercept plus the slope times our explanatory variable. In conclusion, this video focused on the special case when there are only two groups and we have the same model assumptions as discussed in the textbook. In this situation, all three models are mathematically equivalent. When we look at the two-sample t-test, we're testing mu1 is equal to mu2. When we're looking at ANOVA, we're testing whether the effect sizes are equivalent. And when we're looking at regression, we're testing whether the slope is equal to 0. When the models are mathematically identical and the assumptions are all equivalently met, you will get exactly the same p-value in all three cases.